Thank you so much, and thank you for the invitation and the honor of speaking at this fantastic event. So this is where I work, or this is a picture of an ICU. It's an environment that I know some of you in the room are very familiar with, others are less familiar with. And just to orient you, there's a lot going on here, obviously. Somewhere beyond all of this, you can see buried in the background, there's an actual patient who's being cared for by a doctor, a nurse, and a whole host of machines. There's IV pumps, there's a dialysis machine, there's a ventilator, there's an electronic medical record that you see on the side there where someone is charting a bunch of information. And so 10, 15 years ago, when we started kind of getting really interested in how machine learning might help improve the care of these very critically ill patients, we thought this is a great, this is a target-rich environment. One, there's lots of problems here that need to be solved. But two, there's tons and tons of data. And all of these systems require tons and tons of data in order to operate. That's kind of where that phrase, that data is the new oil, comes from. It fuels everything. So the data is in all shapes and sizes and all sorts of forms. This is a paper this was a couple of years ago now. Yeah, this was in Chest in 2018 from a guy named Nelson Sanchez Pinto, who's a informatics pediatric intensivist, and Matt Cherpek, who's an adult intensivist in the States. And they started to kind of map out the space of big data in the ICU. And as you can see, it comes from tons of different sources. And the ones in the dotted lines there are from EMRs. The others are from other spots. Some of them are more easy to come by than others, but obviously we are awash in information from electronic medical records now, diagnoses, vital signs, lab work, demographics, all these sorts of things. All of those machines in the ICU generate more data still, so we get waveforms from the monitors. You know, there's everyone in the ICU is connected to a monitor. That's the machine that goes ping, and that has all of the little waveforms on it, your heart rate and your oxygen levels, and often your blood pressure and all these sorts of things. Those are recorded at high frequency, like 500 hertz recordings, which means that every second you get 500 data points. And if you do that on every patient in the ICU 24/7, obviously that's a lot of data too. Patients in the ICU get lots of x-rays and CAT scans and stuff done, so there's lots of radiology imaging. And sometimes they even get genomic tests done, and there's a whole bunch of information from that standpoint. So to tell kind of a tale of AI in the ICU in 3 acts, this would be Act 1. This was, in years past where we were trying to get a sense of what the landscape was here. And when I came to Queen's about 10 years ago, we had grand visions of doing this, and this was my schematic that I had submitted to a big NSERC grant that was going to fund this huge project to basically collate all this data and put it into one place where we could query it and apply machine learning algorithms to learn all kinds of important and useful things about what's going on with our patients in the ICU. Why are they sick? What's likely to make them better? What's likely to happen to them in the future? And we were shortlisted, but we just missed out on the funding. But in the interim, we've managed to do a lot of these things. We've done a lot of interesting work looking at genomic data from patients in the ICU. So, we get a sense of what their inflammatory conditions are like, or their immune system activation is like, by looking at their blood work that we do in the hospital. But we get a ton more information when we actually look at how all of their genes are transcribed at any one particular time. And that becomes a big data problem, and we have machine learning algorithms that have been really helpful in kind of giving us some information in that way. Similar stories with the large volumes of EMR data that are available, and some of the physiologic data that are available. So in the first kind of iteration of this, we were basically grasping at all of these data sources to try to get them together and wrench them into these machine learning algorithms to try to get some information out. So maybe Act 2 is where we're starting to maybe get kind of good at this and get better at this, and that's mostly because of 2 things. One, our colleagues in computing have really moved the ball down the field tremendously in terms of the algorithms that can do this, and we've gone from relatively simple machine learning algorithms to things like deep learning, where there are much more sophisticated models that can take much more data and generate very interesting insights from it. So this is from a collaboration with a number of people, mostly Parvin Mousavi in the School of Computing here, but also Stephanie Sibley, who's my colleague in the ICU and is an expert in atrial fibrillation, where we were able to take data from our ICU, from the monitors, those ECG signals, and deploy these deep learning models to classify whether people had atrial fibrillation or not. And this is a heart rhythm problem that is a frequent problem in the ICU. Patients who may come in with a normal heart rhythm just because they're so sick and they're getting so many treatments and they're on all of these machines. The stress of that can cause them to go into this abnormal heart rhythm, and that abnormal heart rhythm has consequences. It increases their length of stay in the hospital, it increases their mortality risk, it probably increases the risk of them having strokes and heart failure in the months and years afterwards. So being able to diagnose it is obviously really important, and being able to predict it is obviously even better, because if we can predict it, then maybe we can start to run some clinical trials about interventions that we think might be able to prevent it from happening in the first place. And so the team of students and experts that work with Dr. Maslove were able to take some of our data and actually pretty accurately identify whether someone was in atrial fibrillation or not, based on these signals from the ICU, which are much noisier than the signals that we get when you're just getting an ECG done in the ambulatory clinic. These numbers here will be familiar to some of you and less familiar to others. Basically, it means that the algorithm works really well. It can successfully identify or distinguish a normal heart rhythm from this abnormal heart rhythm. And so Act 2 of this kind of project and long-term undertaking is starting to get better at this, and as we sort of progress here, we're poised and positioned to get even better still through the use of newer machine learning models, things called foundation models that are much more general in how they learn, and we're working on this now and seeing some great results. So up until this point, and there's always debate around what's machine learning and what's artificial intelligence, and maybe we'll touch on that a little bit further. I think for a lot of people, machine learning is just a way where we can use math to identify patterns and use data to drive that. We get into the realm of true AI when those algorithms or those systems are maybe making decisions or creating something new. But up until this point, it's mostly what you might qualify as machine learning. And the science and the research has progressed in a pretty linear path and in a way that we sort of recognize for research from any type of research, be it in any field. We knew what the problems were. They're the same as problems in any field. We need more resources because the computers are more expensive and fancier, and we need more energy to power the computers, and we need more data to power the algorithms, and we need to apply for grants for these sorts of things. But we kind of knew that the more we refine these algorithms and feed it more data, we're going to get to this point. Act 3 is a bit of a different story. And I think that's where we start to really think of where the rubber meets the road in terms of artificial intelligence as opposed to machine learning. And you saw something similar from Dr. Barber's talk as well, because I think this is on everyone's minds. Act 3 started, just in the last few months, really, where we have started to explore the capabilities of true generative AI. And that's set us on an uncertain path. And it's not solely related to the work that we're doing in machine learning and predictive modeling in the ICU. This is a lot more fundamental, and it really impacts the way we do science and we do research in general. And so I look at this with great interest from the standpoint of another hat that I wear as a journal editor, and looking at the ways in which we traditionally have communicated research, which is this centuries-old system of peer review where people get funding, they do their experiments, they write up their experiments into manuscripts, send them to journals. Journals send them out to be reviewed by a panel of experts, and they get published, and everyone gets a round of applause and promoted. And this new era that we're entering into, I think, has implications for anyone doing research along those lines. And it really was brought to light for me when I was talking to the MD, PhD students here just a couple of weeks ago. And if you've ever spoken to someone who's doing a PhD off the side of their desk while they're in medical school. You can imagine these are really bright and motivated people, so it's quite an interesting conversation to have with them. But we just kind of chatted about how they're using this, because this is new to me too, right? This is kind of new to everyone. And I think there's a lot of work to be done to just socialize these concepts and what it is that people are doing with this, and is it okay, is it not okay? There's lots of trepidation around that. But basically, we sort of explored ways that, when we used to do literature searches, if someone was starting their PhD, starting a research project, they would go to Google, they would go to PubMed, they would type in kind of a clunky search phrase and get a list of articles that they would then go through and read. They don't do that anymore. They open this window, this is ChatGPT, or Claude, or Grok, or any of these other ones, and say, hey, has anyone ever looked at X, the thing that they're interested in looking at? And instead of getting a list of articles, it gives you this succinct answer with references so that you can go and check on them, and you're sort of off to the races a lot quicker. And then, of course, you can tell this machine, okay, great, I'm going to do this, take these points, and now write an introduction for me for my thesis, or develop some methods for this project, or write me a grant. Here are the specifications of the grant. This is a CIHR grant. The funding is this much. The term is this long. We need to meet these metrics. And what used to take many, many months or years of grant writing is kind of at least giving you a start in a very short period of time. They use this, and I've done this recently myself, to not only debug their code, but write their code. Everyone doing research now is using statistical software or other computer languages to do stuff. And debugging code used to be very laborious. It got a lot quicker when you could Google the error phrase you were getting and get some community answers. Now you just take your junky code, put it into this window, and it returns clean code to you, which is quite amazing. You can, if you don't like to get your information by reading, you can get Google Notebook LM to create a podcast for you. You take the document that you're trying to read, or even a series of documents that you're trying to read, drop it into this AI, and say, create a podcast of two people talking about this subject, and you get a podcast of two people talking, and it works. You can create research budgets, you can create figures. I need to show me how the calcium channel interacts with X, Y, and Z, and it can do that sort of thing. Where things get really interesting, and where I think we all sort of are kind of trying to feel out the situation a bit more, is where this crosses the line, right? So if you can say, write me the introduction, write me the methods, can you also say, write me the discussion, write me the conclusion? Can you say, this journal asked me to peer review a manuscript. You could drop it into this window, say, please peer review this, and it will return a shockingly good peer review report. You're not allowed to do this. This is a prohibition, at least at the journal that I work for. But you'd be kind of betraying the trust of the authors who have entrusted you to look at it yourself in doing that. But it can do it, and do it pretty well. And what's the next step? I need this. Say we needed more ECG data to do this ECG research, but we just are impatient. We can't wait for the patients to come through the ICU to collect all that data. Well, could it create that data for you? It probably could. Will we know that it did that? There are some papers that show that ChatGPT or AIs can make you biopsy images that are indistinguishable, basically, from actual biopsy images, which is terrifying. Could you just falsify a whole research report? And could you even be a nefarious actor who intentionally feeds an AI junk? Because knowing that the AI is going to train and learn from whatever you give it, can you poison the AI that way in an intentional and nefarious way? So that's maybe a very dark and cynical view of where this technology could lead. But I think these are the issues that we're going to grapple with. On balance, there's more green than red here, and to be perfectly transparent, yesterday I was dealing with a manuscript review where a reviewer had said to me, you didn't interpret the results of your logistic regression correctly. And I read it, and indeed I had not. I reported it wrong. And it's not a big deal to do. There's some math, and I can never remember how to do the math. So I copied the the output of the model that my statistical software gave me, put it in here and said, could you, turn this into an odds ratio and make it interpretable? And it did it in 5 seconds. Less, it just did it instantly. And so that leaves us all sort of wondering, that's good, but how much of that can we get to do? So these models will definitely transform the way that we're doing research and predictive modeling in the ICU. We anticipate that we'll soon be pretty good at predicting who's going to develop atrial fibrillation in the ICU so that we can enroll them in studies, prevent that bad outcome, and improve the health of people who are critically ill. But at the same time, I think we've got an eye on where this whole field is going that is a lot less certain than it was even 18 months ago, where we had a clear path that we knew where research was going. This path is changing on a daily and weekly basis, which is very fascinating.